recording is rolling. It is Friday, December 6th. Some things coming up. You guys know there's going to be an in-class quiz coming up this Tuesday. The 10th is going to be on energy and momentum, so 10 questions each. So some conceptual questions. There might be some puzzle type questions, but real basic fundamental type formula setups. You guys can bring in a page of notes. It could be both sides. That's okay. Just like the last in-class quiz, you guys do that. We'll start this midterm review on Wednesday. Actually, I just gave you guys the midterm study guide, a bunch of questions here. So the midterm is going to be in two halves. The first half is going to be 50 conceptual questions, which comes straight off this page. The second half is 10 puzzle type questions. So it might involve some formulas. Right? Okay. If you guys want to do show and tell, this is optional. This is next week. So Friday, if you guys want to bring something in class, share it with classmates. That'll be your opportunity there. All right. There's also, I posted this to Google Classroom. You guys do it next week, Spirit Week. So this is posted to Google Classroom. Also, tape by my door right there. You guys got that too. All right. All right. So you guys know what we're doing? All right. So today we're going to do energy review. And I gave you guys a quarter page with TED Talks. We're going to watch a couple of TED Talks at the end class today. A little bit different, but you guys get to see a little bit application of physics. So energy review. All right. Here we go. So you guys remember I posted an updated version of this book to Google Classroom. I think I got it like right here. Right, so it's the November 2024 edition. Right, so there's a few new slides you guys will see here that did not show up in your thumbnail notes, but here, we'll hit them all. And so I'm going back a few weeks ago. We were talking about energy. Guys, energy is measured in, what does this capital J stand for? Joules, right? And energy can take lots of different forms. And look, they're all in joules. So work could be an energy transfer. Right? We'll look at these different forms of energy, these mechanical forms. Now, energy can also take forms that are not on this page too, like in a AA battery or in food calories, something like that. But oh, and what's this one down here? Power is measured in, what is this W, this capital W? Watts. Right. Let's get a closer look at those units. So 1 joule breaks down into 1 Newton times meter. Hey, that makes sense because you guys know work. Guys, what's the formula for work? Work equals what times what? Force times distance. Yeah, and force is in newtons, and distance is in meters. Put it all together, right? And okay, and it further breaks down like that in terms of kilograms, meters, and seconds. Right? So, hey, guys, can you create joules of energy or destroy joules of energy? No. Right? However much energy there is in the universe right now, same as there was a billion years ago, same as a billion years in the future. Right? So you cannot create or destroy energy, but you can transfer forms. Right? And how about this other one? Watts. You guys ever look on a light bulb? So it's like 20 watts. Well, that would be like 20 joules per second. Okay, so that's a rate of work, right? Rate of energy transfer, right? Joules per second. Okay, you guys got joules and watts for energy and power. Right? Right, here's the main mechanical forms that you care about in this class. Now, I have 6 forms on here, but really the ones you guys care about, especially for this quiz coming up on Tuesday, are just the gold boxes. So I got work is force times distance. You guys just told me that one. That's an energy transfer, right? In fact, if you lift something some height, isn't it true the force to lift it would be probably equal to its weight, and the distance you lift it could be its height? Oh, and that's the next one right here, mgh, mg times h. So if you lift something, put it on the shelf, the work you did lifting it is equal to the potential energy that you just gave it, mgh, right? So that's a form. Now, this green one is the more universal form if you send a rocket to the moon, but we're not going to worry about that one for, well, probably the rest of this class, right? But it's there, right? Right. Ooh, energy stored in a spring. You guys see this 1/2 kx squared? I'm going to flip slides just for a minute here. I'm going way back in this class. You guys remember Hooke's law, F equals kx? Right. Now, these are 2 different formulas, 2 different concepts that students mix up all the time. Is how much force does it take to compress or stretch a spring? Well, that's F equals kx, and that's the graph you guys are looking at. Right. So F versus x, I say F equals kx. Guys, what is K in this class? K stands for spring constant, like how stiff is a spring in newtons per meter, right? Right. So it's a diagonal looking graph for an ideal spring, right? So there's that, there's force. And then there's how much work did it take to compress or stretch the spring? Therefore, how much energy is stored in that spring? And that's the area under that curve, right? So that's this green triangle right here. You guys see this green triangle? And if you run the same variables, it ends up being 1/2 kx squared, okay? That's what it works out to, okay? Right, so force to compress a spring, kx. Energy stored in that spring, 1/2 kx squared. And that would be in joules. Right? All right, so I'll go back here. So you guys got that. And there's one more main one you guys care about, energy of motion, 1/2 mv squared, which almost looks kind of like more recently, you guys remember we did momentum, which is mass times velocity. right? So it has the same ingredients. If it has the mass and a velocity, it has both the momentum and a kinetic energy, just different arrangements of those variables, right? So energy 1/2 mv squared. Guys, let's contrast those two. Momentum is what? Is that a scalar or a vector? It's a vector. So if something's going right or left, that makes a difference if it's positive or negative. But what about this 1/2 mv squared energy? Is that a vector or a scalar? That was a scalar. So it doesn't really matter the direction of motion for that v. Okay. So I'll just call it v speed sometime. Right. You guys good with that? All right. And the screen one at the very bottom is like if a ball is rolling. We'll save that one for January. All right. All right. So we got that. Got that. All right. All right. So work is force times distance. Now that's a dot product, which means you only multiply the parallel components together. For example, if you carry something up the stairs, up this diagonal distance here, it takes work to lift it straight up, but it doesn't actually take any work to carry it across the room. Like here, if I had a long flat table and let's say I have a marble and give it a little tiny tap, point, that marble could roll all the way across the table. And it doesn't take any work to do that like horizontally, but vertically it takes work to lift it, right? So I only care about the components that are, like the dot product. They're both vertical in that case, right? All right, so dot product. So force, distance, cosine theta, if the angle is between the two vectors. If you see a force versus distance graph, then the area under that curve is how much energy was transferred. That's called work. If it's a constant force, that's very simply a rectangle, right? Or if I go back a few slides, I remember Hooke's law was more like a diagonal looking graph, so it was more like a triangle shape. Okay, here's for how much work, right? How much energy, right? Closed and open systems. So at this point in the class, you guys got a few different perspectives on what makes something closed or open. There's a forces perspective. There's a momentum perspective. Here's the energy perspective. Sum of energy initial equals sum of energy final. Okay. So, hey, this is conservation of energy. This is you cannot create or destroy energy. That's all. Okay. Now, my classic open system example is a car braking to a stop. It's going to show up in a few slides. Right, so that's if there is an energy change, but that comes from either work is being done on or by the system. So you can do plus or minus work. Okay. Now, these would all be in joules. Joules plus or minus joules equals joules. Okay. All right. All right. Don't worry about that one. All right. Here's this one keeps coming back over and over and over in this class, doesn't it? Okay. So Galileo drops the ball from the top of the tower. How fast does it crash land? All right. And you guys got a couple ways to solve this. Let's look at the energy method. So, guys, what kind of energy at the top of the tower? Is that potential energy? MGH, which is in fact equal to the amount of work it took him to lift it, put it there in the first place. Right? MGH. Okay. No, the ball falls. Let's ignore air drag. Let's say there's no air drag. Right when it's about to hit the ground, it's like a millimeter above the ground. It has pretty much all what type of energy? Kinetic. That's 1/2 mv squared. Guys, is this MGH at the top equal to this 1/2 mv squared at the bottom? Yeah. If this is like 100 joules here, that's 100 joules there. You can equate those two, and then you can solve for speed if you want. And it's always square root 2gh. As long as you drop it, square root 2gh, right? Guys, which variable completely canceled out? The mass canceled. You see that? So you guys could calculate this if I throw this question at you. All right. Here's sort of the exact reverse question. Suppose you know how fast you can throw a ball and you throw it straight up. How high does it go? Right. Or if you know how high it went, how fast did you throw it? And I wrote that right at the very bottom. Look, it's b equals square root 2gh all over again, right? But here's how high you can throw it. Right? Let's focus on how high you can throw it. Okay. You guys got two different ways to solve it now. Here's the old kinematic way. Here's the new energy way. They both get the same answer. Suppose you got two friends, and one friend can throw 3 times the speed of the other friend. How high can you throw compared to your friend? 9 times, because a factor of 3 on the speed squared is 9 times the height. Right? Is that? This one's new. So if you want this poster, you gotta download the book. Right? But I think you guys did see this question on the last take-home quiz. Right? You guys ever drive over that diverging diamond on Vieira Boulevard over the interstate? Right? Guys, as your car's coasting uphill, is your car slowing down? Yeah, even if there was no frictional losses, that would still be true. Here I'm showing no frictional losses. The car's just coasting. It slows down. Because what kind of energy does the car have at the bottom of the hill? It's all kinetic because it's all in motion, kinetic. Right? Now at the top of the hill, some of that energy turned into what? Potential energy. Got some MGH there. So set up the equation. 1/2 times mass times the speed at the bottom squared equals. And then at the top of the hill, we got some MGH. Now, if the car comes to a stop, then that would be the end of the story. If the car is still moving, I bet it's not moving as fast. So you got a little bit of 1/2 mv squared left over, right? You guys can set that up and solve that, right? Energy at the bottom, energy at the top, it's equal, right? All right. Ooh, here I got 3 kinds of energy all on one poster, the main 3 types. So push this mass against the spring, let it go, pew, flies around the loop. What type of energy at point A? All the energy was in the spring potential. Now, as an energy term, am I going to call that F equals kx or E equals 1/2 kx squared? 1/2 kx squared. There's your energy. And so if you knew k, how stiff is the spring, and x, how much you smashed it, that would give you some number of joules. Let's say that's like 100 joules. Okay, could that be like 100 joules maybe if you run the numbers? All right. Then I need to pick some point B. Let's say at the top of the loop. Pew, by the time it gets up to here, does some energy go into lifting it against gravity? So there's your mgh, and that's some number of joules. And then maybe you have some energy left over, and that could go into its motion. That's 1/2 mv squared. Okay, so let's throw some numbers at this. Suppose you had 100 joules in the spring. Maybe it took 25 joules to lift it up to that height change. How much energy is left over to go into its motion? 75. Yeah, because 100 equals 25 plus 75, right? And then if I told you the mass, you could plug that in and you could solve for V. How fast is it going, right? You guys see that? Ooh, here's another one that's new. This one's new. So what type of energy on top of the platform? Gravitational potential, mgh, okay? And then suppose the maximum stretch point is at point B, and this dashed line is like the lowest height that it achieves, right? Okay. So this bungee cord has this unstretched length L, and then it has this maximum stretch, I'll call X, right? Where is all the energy at point B? All the energy is in the bungee cord, which I'm treating as a spring. Yeah. So the spring of the bungee cord. So I'll call that 1/2 kx squared. K is how boingy is the bungee cord. X is how much it was stretched, right? In fact, L plus X, that is the height change, isn't it? Okay, so that's where, you guys see the original MGH? Instead of H, I wrote L plus X, right? You guys that? Okay, so then if you had some numbers, you could solve that. Right? Does the mass cancel on that one? No, the mass doesn't cancel. Ooh. So if you have a light friend and a heavy friend, be careful about bungee jumping, right? All right. This one is probably too complicated for the Tuesday quiz, but if you're going to take physics in college, then hold on to this one because they're going to ask you this question. Here's a good one. You guys did a lab on this one too. What's the speed of a pendulum at the bottom? Let the pendulum go, swings, right? So this is really the same as the Galileo question. Isn't it all potential at the top, all kinetic at the bottom? And the speed at the bottom is just square root 2gh. Same as Galileo, square root 2gh. Right? And since it's a scalar and not a vector, you don't have to worry about the direction change, anything like that. Square root 2gh. Okay? The extra fun in this one is doing the geometry to figure out what is that height change based on this L and this theta. And so, so you guys see how that works. Right? It's like that. And then one more fun twist you could put on top of that is, what if you gave it a push? Then it would also have some kinetic energy at the beginning. I skipped some algebra steps here, but this is how it shows up at the end. Right? So if you ever see that in the future. Right? Here's the lab you guys did. You guys calculated, and then you guys measured with the speed gate empirically. What is the speed? You say, hey, look, it's the same speed. You got 1.9 meters per second, 1.9 meters per second. It's the same. Yeah. Right. Here's my classic open system. A car brakes to a stop. Guys, what kind of energy did the car have at the beginning? Kinetic. Yeah, it was a motion. So I write that down, 1/2 mv squared. Right? How much energy does the car have right at the end? 0 joules. 0 joules. It's not moving. There's no kinetic. Didn't go up any hills. There's no potential. 0 joules. Where'd all the energy go? Into work done by friction. So I'll call it force times distance to make that an energy type term, right? Right. So kinetic energy started out with minus the work done by friction goes to 0, right? And then I can, do some math and solve for some stuff, right? At the bottom here in gold boxes, I have braking distance as a function of starting speed, right? Hey, take a look at that answer, that whole nice looking fraction right there. Which variable completely canceled out? The mass of the car. So if you have a light car versus a heavy car, do they have the same braking distance? Yep. If they have the same tires, same road, same initial speed, yeah, same braking distance. That's a good classic physics question. How about this? Suppose you have a slow car versus a fast car. What if you have a car that's going 3 times the speed of another car? What happens to the braking distance? 9 times the braking distance. There's a factor of 3 squared. That's 9 times the braking distance. Ah, right. How about you speed up the car from rest? You get up some speed. It takes like a gallon of gasoline. You say, hey, what if I wanted to go 3 times the speed? And you start the car from rest again to get up to 3 times the speed. How many times the gasoline does that take? 9 times, because it'd be 9 times the energy, wouldn't it? To get to 3 times the speed. All right. Ooh, Atwoods. Now, you guys saw Atwoods way back in dynamics days. I had to guess what's the acceleration and what's the but this poster, I don't see anything about acceleration at all, although it is accelerating. I see how fast maybe does it move at the end of some height change. I don't see any mention of time. This is not the only way to solve this one, but this would be maybe the fast way. All right, let's think about this in terms of energy. So do you guys think the large block is going to be falling and that's sort of providing gravitational potential energy, MGH? So I wrote that in green right here. And then where does that energy go by the end of that motion? Well, I'm thinking 3 places. You have to lift the small block. So that's this MGH here in blue, lifting the small block. So that consumes that energy. Okay. And also at the end of that motion, those blocks are moving. So they each have a 1/2 mv squared. So you add both of those terms. Okay. Here's that. So like energy supply, energy demand. You guys can do that. Okay, do that. All right. Here's a modified version. This one's really similar. The only difference is this top block is not changing elevation. Right. So this block on the side is falling. That's supplying the energy. That's what's making everything move. And it's giving each block a speed. Okay. All right. Here's a little bit fancier. If you throw some friction in there, it looks like that. This one I pulled out of the college physics textbook. Okay. All right. Ooh, do you guys remember pulley systems, mechanical advantage, simple machines? All right. Here, let's do an example. Suppose this object right here weighs 24 newtons, right? 24 newtons. What is the tension in the string? What's 24 divided by 3? 8 newtons. How much force do you have to pull with to lift it? 8 newtons. Suppose you're really weak. I can only pull with 8 newtons. Can you lift a 24 Newton object? Yeah, you can just lift this. Right? Now, what's the catch? The catch is you have to pull lots and lots of string. Right? Suppose you pull 30 newtons. How much does this raise? Suppose you pull, I'm at 30 centimeters. I pull 30 centimeters. How much does this raise? 10 centimeters, only third as much. So here's the rule. Work output can only be as much as work input. Hey, that's conservation of energy all over again, isn't it? Conservation of energy. Okay, so got that. All right. Oh, here's the lab you guys did. You can get mechanical advantage with the wheel, mechanical advantage with an incline. Here's a bunch of simple machines, get mechanical advantages you guys can do. Right. You could do a lever like that, like seesaw, right? Get some leverage. Okay. Ooh, power. Now, you guys know power is work over time. Right? So, for example, if you saw a 20-watt light bulb, power is measured in watts, right? 20-watt light bulb, that would be consuming like 20 joules per second. 20 joules per second could be 20 watts. Okay, so I write down that formula, right? Now, let's apply this to this elevator. I have an elevator here. Here's an elevator cable. Do you think there's a motor at the top of the elevator shaft going pull up that elevator? So I'm drawing some power off the electric grid to do that. How much power? How many watts? Let's figure this out. So, guys, what's the formula for work? Work equals what times what? Force times distance. So I write that down, a little substitution. Hey, what is this right here? What is distance over time called? Velocity. So force times velocity. So if you know the force on the cable, and you know how fast the elevator is moving, multiply that together, you get the power in watts at the motor at the top of the shaft, pulling it up. Right, you guys do that? Right. All right, efficiency. Right, so useful workout compared to total work in. Right, maybe get something like 95% efficiency. I think you guys did a lab with the pulleys. I had you guys do this green box version. What's the actual compared to ideal mechanical advantage? Maybe got something like 95% efficiency, something like that. All right, this one, save this one for college. All right, and okay, and that's a wrap on that energy review. All right, so we're gonna do something a little different here. You guys ready for TED? I gave you guys a quarter page for TED. We're gonna flip over to right now.